Welcome back, everybody. Last question we looked at the statistics with discrete variables. Now let's look at an example with continuous variables. This is problem 1.3 out of Griffiths. Consider the Gaussian distribution rho of x is equal to big A e to the negative lambda x minus a squared, where big A, little a, and lambda are all positive real constants. If you haven't seen that script R before, or double struct R before, that's just the real numbers, and we just want the positives out of it. So with that, part A wants us to use equation 1.16 to determine big A. Part B wants us to find the expectation of x, the expectation of x squared, and the standard deviation sigma. Finally, we want to graph this distribution rho of x and see what kind of characteristics it may have. That being said, this distribution is an amazing distribution. We use it and study it in depth in many other areas of science. This is also known as the normal distribution, and soon we will see that a Gaussian integral is anything with an exponential with a negative variable squared. As you see, it has e to the negative x squared in this kind of hidden format, but those integrals are a lot to deal with, and so the author gives us tables in the book for that. And that being said, we will see these a lot, so let's get used to practicing with them. All right, moving on. So for part A of this solution, what we want to understand here is that since we're dealing with probability, part A is asking us to normalize this distribution. What does that mean? Well, normalization is very important to this theory. Due to probability, we know that the sum of all probabilities has to equal once, hence we need to normalize the probability distributions to this fact, i.e., integrate over all possible probability possibilities and set that equal to 1 because we know that the sum has to equal 1. And that's what we see here. Of course, calculus has to come into play when we are evaluating this integral, and we have to use a u sub. As you see, we let u equal x minus a, therefore du is equal to dx. This u sub will also come back when we're finding the expectation value, so don't lose sight of it yet. Once we do the u sub, we see that a, again, is just a positive real constant, so we bump it outside the integral. We set that equal to 1. We notice that this is an even integrand over symmetric bounds, so what we do is double it, but instead of having negative infinity to positive infinity, we go from 0 to positive infinity. And what this allows us to do is form match with the tables in the book. So here what we see is the example integral given to us in the book. Integral 0 to infinity, u to the 2n, e to the negative u squared over a squared dx. As you see, this is a crude generalized form, and it's up to us to find out what n and a are for this context. Again, here we've got to be very careful because a is also a parameter in the integral formula, but also a parameter in the integrand that was given. So let's just be careful on our bookkeeping. The reason why we have to find it is because we see on the other side of the table, we see what the integral is expressed as with the square root of pi, and so clearly, as you see, we need to find n and a. How do we find n? Well, what we need to do is match the u's. So in general, this is whatever the independent variable is that we're trying to tinker with, and we see that our integrand has u to the 0 power since the leading factor on the exponential is just 1, u to the 0 is 1. So what we do here is say u to the 0 is equal to u to the 2n, and so if we just get rid of the u's, we see that 0 equals 2n, and therefore n equals 0. Check. Now, similarly, if we want to match the exponentials to see what the arguments are saying, well, we see that our exponential is negative lambda u squared, and theirs is negative u squared a squared over a squared. You see that the u's cancel, the negatives cancel, and the exponentials are canceling, so we're just comparing the arguments. What this tells us is that lambda has to equal 1 over a squared. If we solve this for a, we get a is equal to square root of 1 over lambda. Okay, not too bad. Now what we need to do is plug these parameters in and we see that on the next page. All right, so plug these newfound values into the form yields. Well, now we just plug these parameters in and simplify. Okay, so you see the N, when we color coded the green to green, N was 0, A is in blue, and so now we're just evaluating the right hand side of the table value and solving away at it. So with that, you see it simplifies kind of nice. The 0 factorial over 0 factorial cancels out. That's nice, not always guaranteed. This 2 and this 2 cancel out due to the fact that 2 times 0 plus 1 leads to an exponent of 1, so we only have one factor of 1 over 2. That's nice. Eventually, we can just consolidate the square roots due to their properties, and we get square root of pi over lambda. Easy enough. What we have to understand here, however, is that this is all equal to 1, and we need to solve for a. So divide by the square root, which we do here, and we see that we get 1 over square root of pi over lambda, which we know we can simplify with reciprocals. And so finally we get to an answer of a equals the square root of lambda over pi. Wonderful. This guarantees that for whatever factor lambda is in the Gaussian distribution, that our a will normalize that to 1, because that's, again, part of probability theory. We all have to add up to 1. Now moving on to the expectations, remember that last time with the discrete variables, we multiplied the incident event j with the probability of j happening. Here, we do that in a slightly more extended version, a generalized version, which is a natural extension, except we use the independent variable with the probability distribution itself. Okay, and that's what we have here. The expectation of x is all of sum over all probabilities due to the integral dx and a probability distribution, except now we have an x factor here. Okay, so that's a quick, easy, natural extension, and this is where that u sub that we used in part A comes back. We apply the u sub again to the exponential, but then we solve for x using the u sub. So if u equals x minus a, solve that for x, we get x equal u plus a, and that's why we have a u plus a here due to the x down there. Otherwise, the bounds are the same. Evaluate them at plus or minus infinity. You get the gist. Calculus comes back again, and we see that we get a split integral, which is easy. Let's pay attention to what we see here. This now turns into an odd integral, or not, excuse me, an odd integrand. This stays as an even integrand, and we kind of already did this in part A, just with an extra factor of little a there. So let's move on and see how these simplify. All right. So as we know, an odd integrand over an even symmetric bounds lead to 0. They cancel out perfectly. Wonderful. And then we see we just did that integral in part A, except now we have little a attached to it. So what can we do? We can plug in the normalization constant for a, seen in green, which we know is lambda over pi, and that cancels with the pi over lambda, and we're just left with the expectation of x is equal to a. And that kind of makes sense. The reason why is because if I pick any spot in the distribution, this distribution is centered at a, so it makes a lot of sense why we would be expected to find a, because that is the most probable. The Gaussian distribution, being a normal distribution, is centered at a based on the form given to us in this context, so it makes sense that our position is where the most probable is, which is where the distribution is centered. So that's a nice conceptual check there. Wonderful. Moving on to the expectation of x squared, it's just a rinse and repeat, right? So you plug it in, you plug the u sub in, you get u plus a squared, a little more algebra, a little more calculus, but you split them up again. Here you see we're going to have to form match this time with u squared instead of u to the 0, so our n equals 2 equals in 2n, so n equals 1. And that's why we have these factors out front, where a 1 over 2 lambda square root of pi over lambda from the integral of, once you plug it in to the integral form. And then you get a squared this time instead of a, but again we get the integral that we've already seen before, this thing, and we solve that in part A, so we're just using those results. With that being said, the normalization factor cancels these two factors because you factor them out and they cancel. And this gives us an expectation value of x squared of a squared plus 1 over 2 lambda. So with that being said, what is the standard deviation, or rather, what is the variance in the standard deviation here? What parameters does the variance in standard deviation depend on? Comment below and let's have a discussion. Part C wanted us to graph this, and I'll do this in a separate video because I want to highlight some of the parameters of this distribution and show you some cool things with it and how to use modern tools to help us visualize these pretty quickly. So with that being said, I will see you on the next one. Thank you.